We are jumping into a deep dive today that takes one of physics' most iconic demonstrations, Young's double-slit experiment, and, well, slams it right into modern material science.
It's a really fantastic collision of a classic idea with brand new tech.
Absolutely. We've all heard about this experiment, proving the wave nature of light and electrons, even big C60 molecules.
Right.
But our sources detail something completely new, doing this experiment with mechanical waves. Specifically, gigahertz surface acoustic waves, or SOFWs.
That's right. And our mission here is really to unpack the physics of this specific demonstration, because it's not just any material. They're propagating these SOFWs across a gallium arsenide crystal, GaAs.
And that material is the key, isn't it?
It's the whole story. See, SOFWs are these tiny mechanical vibrations that just skim along the surface of a chip. Because they're in the gigahertz range, their wavelength is just microns long.
Which makes them perfect for miniaturized electronics.
Exactly. For filters, and especially for next-gen quantum tech, where you need to, couple energy to qubits.
So we're talking about quantum-level effects on a chip you could literally hold on your fingertip. Before we get to the weird results, just walk us through the setup. How do you even build a double slit for surface waves?
Well, you need incredibly precise tools. To get the wave started, they use something called an interdigital transducer. You can just picture it as a tiny acoustic comb on the chip vibrating at 996 megahertz.
And the slits themselves?
For the slits, they had to literally carve these tiny grooves into the gallium arsenide substrate using a focused ion beam.
FFP, right. It's like nanoscale sandblasting.
That's a great way to put it. It's that precise.
Okay, so that sounds delicate. But here's where I think the real complexity comes in. Why was using SOFWs on a material like GaAs such a challenge? I mean, compared to just shining a laser through two holes. The geometry is simple, but the medium is obviously not.
You've hit on the core difference. It's one word. Anisotropy?
Anisotropy.
Yeah. If you shine light in a vacuum, its speed is constant. It doesn't matter which direction you point the beam. But GaAs has this crystalline structure, a zinc blende lattice.
Okay.
So when a mechanical wave travels across it, it's actually feeling the different densities and stiffness of the crystal depending on the angle it travels.
So you're saying the wave speed actually changes based on its direction. It's like the difference between skating on perfectly smooth ice versus, skating over a surface that has a grain to it, like wood.
That is the perfect analogy. The path of least resistance changes depending on which way you're going. It fundamentally changes the rules of wave propagation.
Which must make it a nightmare to model.
A total nightmare. All the simple math from the optical version goes out the window.
So if the wave is being subtly nudged and pulled by the atomic structure underneath it, how on earth did they manage to measure the interference pattern? I imagine there's a lot of acoustic noise on a chip running at these frequencies.
That was the main technical hurdle, yeah. They used an optical scanning interferometer, which can measure the tiny physical displacement of the surface. But the real breakthrough was applying a pretty sophisticated spatial Fourier filtering technique.
Okay, so a filter, like noise-canceling headphones for physics.
Sort of, yeah. It let them strip away all the unwanted background signals, like waves traveling through the material instead of on it. It let them isolate just that faint interference pattern they were looking for.
Okay, let's unpack that pattern then. What happened to that classic symmetric interference pattern when the wave speed starts depending on the angle?
This is where it gets really cool. They saw two major effects that had, until then, mostly been theoretical. First, beam steering. The central bright spot, the main peak of the pattern, was physically shifted away from the center line.
Wait, so the waves didn't even go straight, even though the slits were aimed straight ahead?
Nope. They were actively being steered, pulled toward the crystal's preferential axis, the 110 direction. The crystal itself was acting like a tiny rudder.
Wow. Okay, what was the second thing?
The second was pattern reshaping. The whole interference pattern was sort of horizontally compressed. The fringes were closer together. The whole thing just narrowed.
And this was all because of the material?
All because of the material. And what's crucial is they found the pattern was incredibly sensitive to this. A variation of less than 1% in wave velocity based on the angle was enough to create these big changes.
So that sensitivity proves you just cannot ignore the material properties.
You absolutely can. And the fact that their filtered measurement lined up reasonably well with these specialized anisotropic simulations is the proof. If you're going to model these next-gen acoustic devices, you have to build in the material's directional properties from the start.
So what this means for you, the listener, is that for the next generation of acoustic sensors or quantum components built on these kinds of crystals, the performance and wave patterns are just incredibly sensitive to the material's underlying structure.
Right. And connecting this to the bigger picture, this demonstration really confirms the fundamental wave nature of SAW-Ws, even in these messy, complex conditions. And, that leads to a final provocative thought.
Let's hear it.
Given how incredibly sensitive this interference pattern is to tiny local variations in wave velocity, how might we be able to invert this whole process? Could we use it to precisely map out the mechanical properties of other exotic materials and maybe pave the way for designing far superior acoustic sensors?